After watching this video lecture, students will be able to define solubility product constant, or the Ksp, versus solubility equilibrium. Students will be able to calculate Ksp from solubility data. They'll be able to calculate solubility in the presence of a common ion. Students will be able to determine how pH affects solubility for specific processes, and you'll be able to utilize ion products, or the Q values, to determine selective precipitations. So basically, guys, Ksp, or your solubility product, is a new K. All right, and what that new K is representing here is basically the solution process, or the dissolving of a salt into water. So we have Kf2 here, solid, breaking into its calcium 2+ ion and fluoride ions in solution. Okay, so we write our Ksp with the species that are allowed to be present in an equilibrium expression. Okay, so our Ksp here, notice it only contains the calcium and the fluoride ions because, once again, solids are not included. So guys, Ksp is known as the solubility product constant, or just the solubility product. Please do not confuse this with solubility or solubility equilibrium. Solubility is obviously referring to your concentration values, so your molarities. And so now that we've defined those two, let's talk a little bit more about some features associated with Ksp. So for Ksp, guys, the amount of solid and the size of particles, pulverized, ground, etc., are not going to affect the position of the solubility equilibrium. Okay, so Ksp, guys, is a constant. So we're not going to have a different K value if we adjust the quantity or the size of the particles, what have you. So let's go ahead and do a practice problem where we're calculating Ksp from our solubility values. So they told us that they've dissolved solid silver chromate into water to give them silver ion and chromate ions, as seen in the following equation. Now they've told us that they've analyzed the equilibrated solution, and that they determined that the concentration of a silver ion is 1.3 times 10 to the negative 4th molar at equilibrium. So what they want us to do is they want us to calculate Ksp. So we're going to plug our information that we have into our ice table, and then plug that into our equilibrium expression. Okay, so we're going to go ahead and write our equilibrium expression for this, and then plug the data in. So our equilibrium expression includes both the silver and the chromate ion, but excludes the silver chromate solid, because solids do not show up in equilibrium expressions. Now, we don't know the initial concentration of silver chromate, but we're going to assume that initially there are going to be 0 ions present in solution, okay, because we haven't actually undergone the solution process. Okay, we know, though, that as that solid dissolves, we're going to end up increasing the quantity of our silver and chromate ions respectively. Okay, and notice there's a 2x here because the coefficient. And so now what we're going to do is we're going to look at our equilibrium values. Now we've been told that the equilibrium concentration of our silver ion is going to be the following. Okay, so we can utilize the relationship that we have here to figure out what x is. Okay, so 2x is going to equal 1.3 times 10 to the negative 4th. And if we solve for x, we're going to get 6.5 times 10 to the negative 5th. Okay, and that also corresponds to the concentration of our chromate. Okay, and so we have that to plug in. So now we have both of our concentrations of our ions at equilibrium, and those will get plugged into their respective positions in the Ksp. So now that we've plugged these in, we're going to plug this into our calculator, do the math, and that's going to give us 1.1 times 10 to the negative 12th as our Ksp for this specific solid. Okay, so basically, guys, what you may find kind of bizarre is that we've been ignoring any of the concentration values of our solid, but remember, the solid doesn't show up in the equilibrium expression, so it doesn't particularly matter in this type of calculation. Okay, so in this problem, guys, they want us to calculate the solubility from our Ksp value. So they've given us our Ksp, and basically they want us to figure out the concentration or the solubility of LaF3 in water in moles per liter. So we're going to need to set up an ice table and, of course, our Ksp expression. So we're going to set up our Ksp expression really quickly here. Okay. And after we do that, then we'll plug all of our values into our equilibrium expression. All right, so what we're going to do here is basically we're going to make some assumptions. Okay, so x, and then we have 0 concentrations of those ions initially, and change of x, change of the following values, and then we're going to assume 0 concentration of LaF3 at equilibrium, and then obviously our following values for our La3 plus and our F minus. Okay, so we plug those concentrations in at equilibrium. So we're going to end up with x, and then we're going to end up with 3x cubed. Okay, and then we know our Ksp here, so basically we're going to manipulate this equation. We're going to end up with 2 times 10 to the negative 19th is going to be equal to 27x to the 4th. Okay, if we divide out that 27 and solve for our x is going to be equal to 9.27 times 10 to the negative 6th molar. Okay. This value is going to correspond to the solubility of our LaF3. Okay, so this value here that you just calculated corresponds to what actually dissolves of the LaF3 when you put it into solution. So the ability of a solid to dissolve is able to be affected by the presence of a common ion in solution. So if I take this particular salt and place it in pure water, its solubility is going to be 1.3 times 10 to the negative 4th. Now, if a common ion is present, the solubility value decreases to 9.0 times 10 to the negative 10. So just like other processes we've seen in the past, solubility of a solid is going to be lowered if the solution already contains ions that are common to that particular solid. Okay, and that's what we would expect. It's just a simple common ion analysis. So keep that in mind, that presence of the common ion will also affect the ability of your solids to dissolve. What they want us to do in this problem is calculate the solubility of a salt when a common ion is already present. So if we go ahead and we look at the salt, CaF2, that'll ionize into calcium 2 plus and 2 fluoride ions. And we're placing this CaF2 into a solution that already contains sodium fluoride. And the fluoride ion is the common ion that's shared between our solid and obviously the solution. Okay, so basically, guys, what they want us to do is they want us to figure out what our solubility is of this particular solid. Okay, so we're going to go ahead and set this up in our ice table and write an equilibrium expression or a Ksp expression for it. So now that we've set up all of our features in our ice table and written our equilibrium expression, let's go ahead and talk about it a little bit. So what we're trying to figure out is x. We don't know what the solubility of calcium fluoride is. We know that initially we don't have any calcium ion present, and that our fluoride ion is present because we are adding this to a solution that already contains sodium fluoride. Okay, our changes are going to occur as the following, and of course our x values at equilibrium will change respectively to what was present initially. Okay, so also we're including the 0 here just because we're assuming that whatever is soluble will ionize completely into the ions. Okay, so now that we have our values at equilibrium to plug into our equilibrium expression, we're going to go ahead and do that. So now that we've plugged these in, we can go ahead and start approaching solving this problem. Now, of course, we could FOIL everything out and solve for x the long way, but we're going to see if we can drop our x's, okay, and then proceed from there. Okay, so if we go ahead and plug in these values, we get the following equation, and if we go ahead and we solve for x is going to equal 6.4 times 10 to the negative 8th, okay, molar. All right, now of course we need to check if this assumption that we made with x is appropriate, so we're going to compare that to our 0.025 molar concentration of the fluoride present initially, and that actually ends up being a valid assumption, okay, with less than 5%. So we can go ahead and say that our x here is equal to the solubility of CaF2, Okay, so our CaF2 solubility is going to be 6.4 times 10 to the negative 8th molar. So we're going to go ahead and look at pH and solubility with respect to our solids dissolving in solution. And pH really can affect solubility depending on how it interacts or how it behaves with the species that are present. Okay, so with this particular process, what we're going to do is we're going to take the solid, we're going to break it up into the stuff that it would dissolve into if it did dissolve in solution, and then we're going to think about how the changing of the pH by the addition of hydroxide or the addition of H plus would alter any of the species present. So if we increase pH, meaning we add hydroxide ion, what we actually end up doing is we increase the amount of this product. Okay, so based on Le Chatelier's principle, if we increase the amount of this product, equilibrium is going to shift back towards the solid. Okay, and basically you're going to decrease your solubility. So basically like a common ion effect. If we decrease the pH by adding H plus, what ends up happening is that H plus is going to react with H2O to produce water in a neutralization process. So basically that's like taking hydroxide ions out of solution. So we're going to produce more product because equilibrium is going to want to shift to the right to replace those hydroxide ions. Okay, so that's going to increase the solubility. So in this particular case, the pH of the solution simply causes shifts left and right relative to the hydroxide ion. Okay, so continuing on with the pH and solubility analysis, let's go ahead and look at another example here. In this case, we have silver phosphate dissolving into its ions. Now, if we decrease the pH or add H+, what's going to end up happening is solubility is going to increase because PO4 3- is the conjugate base of a weak acid. And because it's the conjugate base of a weak acid, we know that it will behave as a base. So when we place the H+ into solution, this base is going to want to interact with that H+. So effectively, you're producing HPO4 and subsequently removing some of this ion from solution. So equilibrium is going to shift to the right, and solubility is going to end up increasing. So if we look at another example, another silver-containing salt, it breaks up into Ag plus and Cl minus. Now in this particular case, if we do the same change, we decrease the pH by adding H plus, solubility actually isn't going to change. And the reason why is because when I add H plus, this Cl minus is not going to behave as a base. And that's because it's sourced from a strong acid, it's the conjugate of a strong acid, and subsequently doesn't behave as a base in solution. So there aren't any species that want to react with the H+. So solubility for this particular substance is going to be unaffected by the addition of H+. Okay, so let's go ahead and look at the ion product Q. So we've already seen Q before. Basically, Q, guys, is just like our K value, except we plug in initial concentrations of our ions. So in this case, it's dealing with Ksp, so it'll be a little bit different than some of the others we've seen in the past, but same thought process. And what we use Q for is to consider whether or not we're going to form a solid. So basically, the reverse process, is it going to predominate, or is this solubility process to the right actually going to occur? So our Ksp and our Q expressions, notice they look the same. The only difference is the not values. That's indicating the concentrations that are being plugged in our initial. And we plug in those initial values. We can then compare our Q to our Ksp after we do the calculation. And if Q is greater than Ksp, then precipitation is going to occur. So basically, and so what's going to happen there is that the ions that are present will come together and form a solid. And so basically that'll continue to happen until the concentration of the ions have reduced sufficiently to make it where Q and K will end up being equal. Now, if Ksp is greater than Q, then no precipitation is going to occur. So the comparison of these two values will allow us to decide whether or not what we have in solution or what we're combining is going to cause precipitate. So we're going to compare Q and K in this particular problem. They're wanting us to determine if a precipitate is going to form when we mix lead nitrate and sodium sulfate. Okay, so when we mix lead nitrate and sodium sulfate, what we get is a double replacement reaction as follows. Okay, so we can see that this is the double replacement reaction, so lead sulfate is what's going to be produced. Okay, so guys, in this particular case, we are concerned about the precipitate that will form, which is PbSO4, and the ions that are related to that precipitate's formation. Okay, now we know that PbSO4, the solid, if we put it into water, the ions that it will break into are the following. Okay, so we have these species here, and what we need to do, guys, is we need to figure out if these initial values that we've been provided of these two ions are greater than or smaller than what is needed to be at equilibrium. Okay, so what we're going to do is we're going to take our Q, our ion product expression, our constant, and we are going to solve our Q value and compare it to the Ksp that they have given us with respect to PbSO4. Okay, so what I need here, guys, is I need the initial concentrations of Pb2 plus and SO4 2 minus, and I can calculate that from the data that they provided. So I'm going to do that now. Okay, so I've gone ahead and calculated our initial concentrations of our ions that are present. So I've taken the molarity of our lead 2 nitrate and the volume that they provided, and divided it by, multiply those together and divided by the total volume of the two solutions combined. That gives us our new molarity of lead 2 plus ion. Okay, I've done something similar to for the sulfate ion, and now I have these initial concentrations of each of those ions, and these can now be plugged into our Q value. Okay, so I'm going to do that. So Q is equal to 6.4 times 10 to the negative 6th. Okay, so guys, now what we're going to do is we're going to compare Q and K. So Q and K, so Q is equal to 6.4 times 10 to the negative 6th, and K is equal to 1.3 times 10 to the negative 8th. So Q is greater than Ksp. And because of this, when we mix these two substances together, PbSO4 is going to form a precipitate. Okay, so basically this is how you progress through figuring out whether or not your your solution that you're forming will actually provide a precipitate. So let's go ahead and look at this selective precipitation. This one's a little different than some of the others we've looked at, but basically what we're going to be doing in this situation is figuring out which ion is going to precipitate out of a solution before another. Okay, so there's a solution that we have. It's containing copper plus ion and lead 2 plus ion. Okay, and what we're going to do is we're going to slowly add iodide ion to this solution. Okay, so we're either going to get a precipitate of lead 2 iodide or copper 1 iodide first. So we're trying to figure out which one is going to give us a precipitate first. Okay, and so we also want to figure out the concentration of the I- necessary to begin the precipitation of each of these salts. Okay, so how are we going to do this? Well, they've provided us with the Ksp values of each of our substances, and they have also given us the relationships, or rather concentrations of our ions in solution. Okay, so basically we know two of the three variables that we need. Okay, so what we're going to do, guys, is we're going to actually write our expressions, our Ksp expressions for each of the species. Okay, so we've written those expressions as follows, based off of what would be produced in solution if these solids were to be dissolved in water. Okay, and then what we're going to do, guys, we're going to plug in the values that we know for each of these. So we know Ksp for each of our expressions here, and we also know the lead and copper ions respectively. Okay, so this will allow us to subsequently solve for our I-. So we're going to go ahead and plug those values in. Okay, so now that we've plugged all those values in, we can go ahead and manipulate the equations and solve for I. So now that we've solved for I for each of these, we're going to compare these values. Remember, as we are adding the iodide ion to the solution that contains both the copper and lead, we're trying to get to a specific concentration of the iodide so that precipitation will occur. As I'm adding iodide to the solution with these ions, basically we're getting closer and closer to the appropriate concentrations needed for the subsequent precipitation of these two species. Okay, and because the iodide requirement is lower for the precipitation of CuI, CuI is going to be the first to precipitate. Okay, because we will reach the appropriate concentration of iodide ion before we reach the appropriate one for the lead 2 iodide. Okay, so copper 1 iodide is going to precipitate first, and then after that has precipitated, then your lead 2 iodide will precipitate.